All right, here's an example of a matched pairs test. Example 1. We hear that listening to Mozart improves student performance on tests. Perhaps pleasant odors have a similar effect. To test this idea, 21 subjects worked on a paper pencil maze while wearing a mask. The mask was either unscented or carried a floral scent. The response variable is their average time on 3 trials. Each subject worked on the maze both with the masks or with both masks in random order. The randomization is important because the subjects tend to improve their times as they work a maze repeatedly. Here are the results. So each row, these two represent one person. These two represent one person, and so on, all the way down. We want to test to see whether the scented masks decrease the time it takes to complete the maze. All right, so here's all of our data. If you want to do this with me, which you should, pause the video and put this data into your L1 and L2 columns on your calculator. Now we need to write a significance test. The first thing that we have is we have to do the hypotheses. Our null hypothesis is that the difference, mean difference, is 0. Because if there's no difference, we're just saying that if we subtract these two values, they get 0. Our alternative hypothesis is going to depend on how you look at this. So when we do these are all dependent on each other. So what we need to do is find the differences of each of these columns. Now, if we could either take L1 minus L2 or L2 minus L1. And it really doesn't matter which one, but how you do it, that will change what our hypothesis is here. So let's think. We want to know if scented masks decrease the time. So we want this number to be less than this number. If this number is less than this number, then things are good. So if this is less, we'd assume that's a smaller number. So I want to do L1, or unscented, minus L2, and hope that's a positive number. Because when I do that, a positive number would mean that this number, the unscented, is bigger than this. And so that means there's a decrease in time for the scented. So if I do L1 minus L2, then this would be the mean time, the mean difference, is greater than 0. So mu, we have to be very specific on our mu here. Mu is the average difference in maze completion time and then you can say by or with scented minus unscented. So you have to be clear what two things we're subtracting. So now we have that out of the way. Now let's look at our conditions. Does the data come from a random sample? I'm pretty sure that answer is no. Data do not come from a random sample. Now, for normality, we only have 21, so we're going to have to graph the differences. So I'm going to go to my stat plot, and I'm going to graph my box plot of the differences. And when I do so, I get a graph. So if this is my x and y, I get a graph that kind of looks like that. I guess we don't really need the x-axis on there. We could just have your 0 somewhere here. And here we can assume normality because the box plot is reasonably symmetric. Or there's no reason to doubt normality, I should say. All right, so that's good. So we can, so now that they're symmetric, now we have to assume independence. So assume each observation is independent. And now we can go on to the calculation. Now, in our calculations, what we first have to do is calculate the p-value, or the x-bar value. So I would go in and do 1var stats on the actual value. So 1var stats, I got negative 0.59. I meant positive 0.595. I typed that in wrong. So we'll start with an x-bar that is 0.956 repeating. And my s of x here is 12.54. And my n is 21. So now we set our anchor at 0. That's our null hypothesis. And if our null hypothesis is 0, how often would we get something that is 0.956 or greater? Well, we would take the probability that we get an x-bar greater than or equal to 0.956 repeating. And this would be a t-distribution because we don't know the population standard deviation. We'll take this number minus our null mean, which is 0, over our standard deviation over the square root of 21. And when we do this, we will get a value of 0.35. Now the probability t is greater than 0.35, we can do a t-CDF, and the probability would be 0.365. That's our p-value. So our p-value is quite high. So now let's interpret this. So for our interpretation, we fail to reject our null hypothesis. Because our p-value of 0.365 is greater than alpha equals 0.05. So now, in the end, if we reject the null hypothesis, we reject this. So in sense, we're saying, or we fail to reject this, so we can't say that's true or false. So we don't have evidence that this is true. We don't have evidence that the mean difference is greater than 0. So we don't have evidence that the scented uh, smell, scented smell, it's pretty redundant. Uh, Scented mask, maybe, decreases maze time. All right.